Hopefully the previous lecture was enough to convince us that it might be worth it to develop some kind of specialized version of our simplex algorithm just for this network application, just for this minimum cost network flow problem. And I guess maybe you also took my word for it back then in the previous lecture that if we develop the specialization for the minimum cost network flow problem, it might be applicable to other variants of this network, of these network style problems. In particular, our real goal isn't specifically this minimum cost interpretation. It's finding some way of applying the simplex method more directly to problems that are derived from graphs, or to use the peculiar terminology that linear programming books like to use, to networks. And so the point of this lecture is basically just to derive some interpretation for the various core components of our simplex method that applies directly to the graph. So instead of talking about, for example, a basis as being a collection of variables, we want to begin talking about a basis as being a collection of edges, because that's what it corresponds to in the network flow problems. And similarly, we're going to begin thinking about the dual of the linear programming formulation of this minimum cost flow problem, and see if we can find a way to interpret those dual variables and dual slack variables, not just as sort of abstract things, as variables that have to exist because of duality, but actually having some semantic intuitive meaning. And then the next lecture after this one, we're going to begin, once we have these interpretations, talking about how do we actually perform the work of the simplex method. So how do we perform, for example, pivots? All right, so here's a network. And we're going to, in this lecture, jump back and forth between a few different examples. Basically, we have to keep juggling small examples for the sake of proving a point quickly versus larger examples for the sake of actually showing something that works. Because it turns out networks that are this small often don't give us enough information to actually understand what we're really seeing. So consider this network here. Back in the previous lecture, we showed that we could, if all we ever care about is solving this with a linear program, we can convert the minimum cost flow problem to this. We can produce this LP. And we also observed, and actually I'm realizing now I've made the same mistake here I did before. I forgot to throw in this non-negativity constraint, which is pretty important. We observed that this LP is sort of unique. There are lots of variants of these network flow problems that have various ways of interpreting things like the balance at vertices, and we often end up with these problems where we have one optimization variable per edge. So for example, this would be the variable corresponding to the edge AB. This would be the edge CB. And we've got one constraint, or maybe more than one constraint per vertex, but we often have these specific sort of identifiable constraints for each vertex that are equality constraints that define some sort of balance. And in the case of our minimum cost flow problems, that's all we have. We've got one constraint per vertex that dictates the total balance of supply and demand has to equalize for every vertex. For other variants of flow problems, there could be other constraints as well. They could even be inequality constraints. But we'll find that a lot of these flow problems have some notion of balance, and that gets implemented in the form of these equality constraints. So in the previous lecture, we noticed that because of the sort of unique structure of these things, in particular, not only the fact there's all these equality constraints, but also because we've got one optimization variable per edge, and because sort of, by definition, a particular edge only is incident to two vertices, we end up with this constraint matrix that's very sparse. In particular, we'll notice each column only contains two non-zero values. In fact, it'll be a 1 and a negative, a negative 1, there's the negative 1, and a positive 1. And so all these things taken together not only give these problems a very distinct form, but we saw a few reasons why throwing this directly into an off-the-shelf solver, although it would work, because we've proven by now that the simplex method in general, if we can put the LP into standard form, we can solve anything with it. Although it would work, it might take a long time, and there might be some features of the resulting standard form LP that really frustrate that solver. And I guess conversely, there are a lot of these network-style problems, and so it would be good to find some way of optimizing the simplex method for those. And I mentioned in the previous lecture, there are also lots of other more general optimizations we could perform. So there are ways of optimizing the simplex method, particularly if we use a linear algebraic interpretation, to optimize a simplex method to work with, let's say, sparse constraint matrices, because we notice this constraint matrix is pretty sparse. There are ways of doing that, but the argument I'm making here is not only for the sake of optimizing this application, but understanding better how we would adapt the simplex method to such a specific situation. I think it's useful to go all the way through and make a special variant of the simplex method, the network simplex method, just for these network style problems. So right off the bat, so the first thing we're going to talk about, as you might have figured out from the title up here, is we're going to talk about what a basis really is. So we know already that each optimization variable corresponds to an edge. So it shouldn't surprise us that our basis is going to have some correspondence to a set of edges eventually. But right off the bat, so I mean, we convert this network to an LP, and we stare at the LP for a minute. We might convert it to equational form or something. And right off the bat, we run into that problem that we saw in the previous lecture, which is that when we have this system that's defined entirely by equality constraints, it's often a better idea to simply not add slack variables, because the primal slack variables end up being completely useless. They have no meaning. They're always equal to 0. So if we do that, if we interpret the system as already being in equational form, we already have this problem, which is that our constraint matrix doesn't have full rank. And the way I'll justify that is I will observe first, as I think we discussed in the previous lecture, if I take the sum of each column, or you could also view this as if I add up every row, what I'll end up with is all zeros. And you might recall from linear algebra that that means that the set of rows of my matrix A is not linearly independent. There is some row that is a linear combination of the others. And obviously that's no good. That means the matrix does not have full rank. And the reason why that's really a big deal for us is if I were to choose a basis of this matrix, so a basis would have to have, well, the matrix itself has 5 rows, so the basis would have to have size 5. If I were to choose a basis and then pull out that basis matrix, let's see. So suppose my basis is, I don't know, the first 5 things. If I pull out this basis matrix, observe that because the sum of each column in the original matrix equals 0, and because my basis matrix is taken by simply pulling out entire columns all at once, then inside any basis matrix that I form, no matter which columns I use, every column will sum to 0. So the rows of my basis matrix will always sum to 0. That means that my matrix AB, so that means that the rank of my matrix AB is not equal to M. So AB will be an M by M matrix, and it won't have full rank. That means that it won't be invertible. And we know already, we talked about this in the previous lecture, we talked about this last week with the linear algebraic interpretation. If AB isn't invertible, we've got a whole ton of trouble. So we need to solve that problem first. This is not even a question of whether our basis will be feasible. It's a question of whether it is a basis, whether we can even do the calculations we want to do. I mentioned in the previous lecture that when this happens, the real reason it's happening is that we have constraints that are redundant. We've got an overspecified system. And so what we could do is either add slack variables. Now, adding slack variables would solve the problem here sort of vacuously. It would pad out the rank of the matrix. It would allow the matrix, these basis matrices, to be invertible, essentially by making the true size of the basis one smaller. That's all it would really be doing. The slack variables wouldn't magically make the system less linearly dependent. What it would do instead was hide some of the linear independence somewhere in exchange for occupying one slot of my basis. So my basis ends up actually being smaller. I think I proved the point in part 1, or in the previous lecture, I think I proved the point that using slack variables for that purpose isn't going to help us very much here. It's useful that they do that in general, but we know enough about this application that maybe we can take a step further and just find a way of pruning down our set of constraints. So our constraint system is overspecified. We've got some constraints that are linear combinations of the others. And the actual reason for this is simply that if I expect that my global supply and demands, my supplies and demands equalize, which is to say that across the entire network, the total balance of supply is 0. So all extra supply is exactly canceled out by all demand. If I expect that to be the case, it turns out that I don't need this number of constraints to enforce balance at each vertex. If I simply enforce balance at all vertices but one, the remaining vertex will have its balance enforced automatically. And I think I can prove that point. Let me see if I can. I'll just go back to this diagram here. So what this is saying, suppose I want to design a balanced flow using this network here. In other words, I want to find a way of completely equalizing the supply and demand of each vertex. And I want to ensure balance so that at the end, every vertex has a total remaining supply of 0. But what if I try this? I'm going to instead say, actually, I don't care about vertex A. Vertex A can have as much supply or demand as I want at the end. I'm not going to enforce that balance constraint at all. So the point I'm trying to prove here is if as long as my original supplies and demands all go to zero, as long as they all add up to zero, I actually don't have to worry about the balance constraint on one vertex because that will come out in the wash. All of the other supplies and demands, when they equalize, will automatically equalize the supply and demand at vertex A. Let's try this. So I'll ignore the balance constraint on vertex A and see what we can do with all of the other vertices. Okay, so let's see. Vertex E has an oversupply of 3. Okay, so I guess I have to send 3 units of flow away from vertex E. I'll make a smart decision and assume that maybe I should send it up this way because it looks like vertex D has a shortage. So I send 3 units up from E to D. Okay, that means the net supply at vertex E is now 0. Okay, so vertex D now only has a shortage of 3. Because I just sent it 3 units. On the other hand, vertex C is getting along pretty nicely here. Vertex C does not need any extra work. It has a net supply of 0. I'm just going to leave it there. Okay, so vertex D has a net deficit of 3, which means somebody has to send 3 units of flow to vertex D. Well, I already took care of vertex E. I already dealt with this edge. So I'm not going to have more units come along this edge. That means that by process of elimination, I have to send 3 units up here. All right, so I send 3 units from B to D. So now D has a net supply of 0. On the other hand, B already had a deficit, and now it has an even worse deficit because I'm sending out units of flow from a vertex that had a shortage. So B now has a deficit of 5. Okay, so somebody has to send vertex B 5 units of flow. I can't have it be vertex C because vertex C is already in equilibrium, and there's nowhere to get any more flow from to make up for that if I take flow away from vertex C. And so I think to myself, oh, wait a minute. Here's vertex A. I don't care about the balance of flow at vertex A. I deleted that balance constraint. So I guess I'll just have vertex A send B everything it needs. Okay, so vertex A sends 5 units of flow to vertex B. And then vertex B is in equilibrium. Great. And remember that I deleted the balance constraint on vertex A. I was ignoring it. But if I erase this, wait a minute. Hey, look at that. Vertex A actually had an oversupply of 5. And that means that by default, vertex A is now in equilibrium as well. So because the whole network, because the supply and demand balance of the whole network was in equilibrium, I didn't actually have to explicitly enforce the balance constraint on one vertex. It doesn't matter if it's vertex A or vertex E. If I choose one vertex and I ignore its balance constraint, and then I work out a complete balance among all the other vertices, that vertex that I was ignoring will actually end up being balanced by default. And so that's the basic idea. It turns out the constraint system is overspecified. I don't actually need to enforce every single constraint to achieve the global balance that I want. So basically what this is saying is if I enforce the flow balance for this number of vertices, and as a notational point, I should add that in graph theory, as you might recall from a previous course, usually if we're talking about the number of vertices and number of edges, we use the variables n and m. The problem is in linear programming, we often use n and m for different things, the number of optimization variables and number of constraints. And in this case, it's extra confusing because the number of optimization variables, which we would normally call n, actually corresponds to the number of edges in the graph, and the number of constraints, which we would normally call m, corresponds to the number of vertices in the graph, which is really ridiculous. So instead what I'll do for this lecture and the next few is, when I want to talk about the number of vertices, I will just use size of v to refer to that. I don't like that notation as much as n, but I think in this case it's good to disambiguate. So what this is saying is, if I simply ignore one of these constraints, if I just wipe it completely off of the matrix, it turns out that by enforcing all of the other constraints, under the reasonable assumption that b sums to 0 to begin with, if I just enforce all of the other constraints, it turns out that that last constraint will get met by default. The system is overspecified. So if I were to just choose a constraint at random and just delete it, then I would end up with a matrix that has full rank. So let's select a some vertex and then delete its balance constraint. And I'm realizing, sorry, I was hesitating there because I see this word and I realize I haven't defined it yet. I'll define it in a minute. So in this course, if we delete any of these balance constraints, we end up with what we want. But although that's an arbitrary choice, it is good to be consistent. So for the sake of consistency, in this course, when I have to go delete one balance constraint, I'm always going to delete the constraint for the first vertex listed, which usually we'll be calling vertex A. So I'm always going to delete that. Maybe the slide spoiled it, but this vertex becomes sort of special. This one vertex without the constraint being explicitly enforced. And so we're going to give that vertex a name. The vertex for whose balance constraint we've deleted, we're going to call that the root. And we'll see in a minute that that means, I mean, you hear the word root and you think of certain things, certain graph theoretic things. And yes, it means exactly that. We're about to talk about trees. So if I delete the constraint row and the entry of B corresponding to that root vertex, I end up with this modified system. And it turns out we can demonstrate that for any connected graph, if I delete one of these constraints, the resulting matrix A prime, which is going to have size of V minus 1 rows, so if I had 10 vertices to begin with, I'm going to have 9 constraints in A prime. It turns out that this will indeed have full rank. It will have rank size of V minus 1. The proof is sort of interesting. I'm going to walk through the intuition behind the proof. I'm not going to walk through the whole proof itself. So, okay, yeah, there's that definition. Whoops. So you can see I shuffled my slides a bit at the last minute here. So this vertex whose constraint was deleted is going to get a special name because it's going to have a lot of significance later when we compute other interpretations of these optimization and dual variables. We're going to call this the root vertex. So this is vertex A. Obviously, we will treat this root vertex as if this constraint is gone, as if we have deleted this constraint. But for the sake of knowing what's going on, for example, remembering the supply value of A, remember that the supply value is actually 5 because we negate the supply when we build up these constraints. For the sake of remembering what's going on, I'm going to keep writing in the constraint that we deleted. I'm going to highlight it in purple like this, so that you know that the constraint is not actually acknowledged by the LP, but it's there so that we remember that we had it there and that we deleted. So we're going to continue writing it down. The other reason that we're going to keep writing it down is that for duality, there's a place where it sort of comes up. Even though if we delete this row from the primal LP, the corresponding column of the dual LP also got deleted. It's good to remember that correspondence anyway. So we'll keep it there, but highlight it in purple, which is our way of saying that it's not that the row should be ignored. It's only there for informational purposes. Okay, so let's now talk a bit more about this interpretation aspect. So in our LP formulation, each arc corresponds to one optimization variable, or more formally, this variable XAB tells us the amount of flow on the arc from A to B in the forward direction, so that we can sort of label it like this. Now, we know that there are cases we saw in the previous lecture where for some reason we've decided it's a good idea to push flow in the wrong direction along an arc. In that case, XAB will be negative. So XAB corresponds to flow in the right direction. So if I'm pushing flow in the wrong direction, XAB ends up negative. And we can already appreciate that that sort of defies feasibility. And that's significant. We'll see that later. But there are times when, just like how there are times when you're solving an LP where you have an infeasible basis just because you have nothing else to work with. You start with some infeasible basis. You might solve an auxiliary problem or something to find a feasible one. We do need a way of modeling some infeasible basis. And it turns out infeasibility does correspond to cases where I'm pushing flow in the wrong direction across arcs. So that's one thing to keep in mind. I also mentioned in the previous lecture that there are these two things that we care about for a flow to make sense. The flow has to be feasible, that is to say all flows have to go in the right direction, but it also has to be balanced, which is to say all of the constraints have to be met. And those are two separate things that we have to enforce. We have to make sure the constraints are met and that the constraints are met without setting any variable to be negative. Those are done separately, and it turns out that it's relatively easier, I guess, maybe interpretation-wise at least, it's easier to put balance as a higher priority than feasibility. In other words, we're going to assume at all times that our flows are always balanced, even if that results in having the flow be infeasible. And so what we'll do is, at each step, we'll say, here's a balanced flow. Is it feasible? What can we do to make it feasible if it isn't? Okay, so once we have this matrix where we've deleted one row, we've deleted the row corresponding to our root vertex, well then we've got this constraint matrix of size of V minus 1. remaining rows. And so any basis to this LP will now consist of, instead of, there were originally 5 vertices, but there are now 4 rows here, any basis will now consist of 4 of these optimization variables. And if we think about this, we realize, wait, an optimization variable corresponds to an edge, so it's sort of reasonable to think of the basis, well, yeah, okay, the basis is a collection of variables, but because each variable corresponds to an edge, I think it's actually quite natural to think of the basis as just a collection of edges. And maybe we could infer some properties that that collection of edges has to have to be a valid basis. And okay, and the slides are asking that question too. What properties do we require for a collection of this number of arcs to form a basis? So remember that when we're talking about a basis, there are lots of properties we need to enforce. I mean, one of them is ideally our basis should be feasible. Certainly we can't run the simplex method unless our basis is feasible. On the other hand, as we saw back when we talked about the linear algebraic simplex method, a basis is still valid even if it's not feasible. But there is a condition that has to hold for a basis to be a basis, even if it's not a feasible basis. And that brings us back to this. So we know that for a basis to be valid, we need to be able to compute the values of our basic variables. And that requires this matrix to be invertible. Now we saw when we talked about the linear algebraic simplex method that this matrix will be invertible for any basis you see during the simplex method. And moreover, if you start the simplex method the old-fashioned way, using a bunch of slack variables where this basis matrix is initialized to an identity, then you're guaranteed for it to be invertible to begin with. But we also saw that there were plenty of cases in the dictionary-based and the linear algebraic method where we could come up with a collection of variables such that the resulting matrix wasn't invertible. And the reason why that was no big deal at the time was that we were able to justify that we'd never actually see that basis in practice. We'd never actually arrive at that basis as the result of a pivot. So we have to consider here, before we talk about a basis being feasible or anything, we have to talk about what does it mean for a basis to be a basis? What does it mean to actually, for it to actually meet the basic, the fundamental criteria to be a basis? So let's work backwards. Each of our primal optimization variables, xuv, is an arc, is an edge in my graph. So why don't I just interpret the basis as being a bunch of edges? Now, this vector here, xb, will of course contain the values of the non-basic optimization variables. And this actually implies something interesting, which is, of course, that if I'm trying to design an optimal flow for my minimum cost network flow problem, then a bunch of my edges will have zero flow. All of the non-basic edges will have a flow of 0, because that's the way that linear programming works. Only the basic, I should be careful. That's the way the simplex method works. There are plenty of linear programs that have optimal solutions where all optimization variables are non-zero. But we know that there will exist some solution where only the basic variables are non-zero. And if we're going to apply the simplex method's logic to this, we should assume that's going to happen in this case too. So what I want then is to compute my vector xb of the values, the flow values for each basic arc. Now to do that, I have to solve this equation, either implicitly or explicitly. So in the dictionary-based simplex method, all semester, we've actually been solving this equation, doing our pivots. We've been solving this equation to find the values of basic variables. We finally saw this in its raw form last week with the linear algebraic simplex method, where we literally were solving this equation with linear algebra. But in order to do this, in order to compute the values of my basic variables, I need this matrix to be invertible. And there are a few ways of approaching this. I mean, we could try and prove that, that a particular collection of arcs results in an invertible matrix or something. But I want to find a way of tying it back into the graph. I want to find a way of looking at the graph and deciding based on a glance, based on inspection, whether a particular collection of arcs is a valid basis. Keep in mind that we don't care if the basis is feasible yet. All I care about is, can I solve this equation? I do not care that the solution to the equation results in non-negative values, just whether I can solve it or not. So there is an interesting interpretation of invertibility that I think really helps us here. I think Van der Bee's book presents it in the same way, not with the same wording, but it follows the same logic, which is if a particular collection of basic, or a collection of arcs is a basis, if this is invertible, if AB is invertible, then for any valid set of supply values, so this is my vector of supply values, any valid set of supply values, there must be a solution to this equation. Because if AB is invertible, then I could just multiply both sides by AB inverse. I wouldn't do that in practice. I would probably solve a system of equations, but symbolically I could do that. So if this is a real basis and this matrix is invertible, then if you give me any valid supply vector B, I should be able to compute the values of my basic variables to balance that supply vector. Keeping in mind, remember this equation here is the equation of solving the constraint system. So it's actually solving this equation here. And the constraint system describes the balance constraints. So I should expect that any set of values of xb that I get by solving this equation will be a balanced flow. It will result in the total flow, the total supply at every vertex in equilibrium, so equaling 0. It may not be a feasible flow, but it must be a balanced flow. So the way I'm going to tackle this is I'm going to say, okay, we now have a condition that's a little bit less linear algebraic that we could check. A particular collection of arcs B is a basis if for any supply vector, assuming of course that the supply values for the whole graph sum to 0, any valid supply vector B, there is a way to compute a balanced flow using only my basic arcs. That's really what this is saying. As long as there is a solution to this equation for any vector B, then the set of arcs I chose is indeed a basis. Okay, there's a lot of words there. So let me go through an example. So here's a network, and I'm going to start out with having everything set to a supply of 0. Now, this means that literally any collection of arcs would balance the flow, because I can just push 0 flow across every single arc, and everything stays balanced. What I want to demonstrate here is that if I choose a particular collection of arcs, and actually I'll get ahead of the example. So this graph has 8 vertices. And we know that once we delete the balance constraint on the root vertex, so A, there will be the size of the basis, so the size of B will have to equal 7. There should be 7 arcs in my basis. Okay, let's choose 7 arcs. Okay, how about these? 1, 2, 3, 4, 5, 6, 7. Okay, there's 7 arcs. So this is at least the right number of arcs to be a basis. So in order to be a basis, to meet this criteria that I laid out on the previous slide, on slide 14, in order to be a basis, there needs to be a way to produce a balanced flow for any valid distribution of supply and demand. So in this case, for example, let's try this. E ends up with a supply of 10. H ends up with a supply of negative 10, a demand of 10. Okay, so can I produce a balanced flow where I'm required to only use the basic edges? So all of the non-basic edges, all of the edges that are not chosen must have a flow of 0. Can I produce, using only the highlighted edges, a balanced flow for these supplies and demands? Well, yes, I can just push 10 here, 10 here, 10 here. And that results in both E and H having an equilibrium. They have a net supply of 0. Okay, what about, but remember that it's only a basis if this works for any distribution of supplies and demands. So how about if I set, let's try setting B to have a demand of 5, or well, we'll start with this. Okay, B has a supply of 5, C has a demand of 5. Okay, that's easy, just send 5 from B to C. Okay, what if B has a demand of 5 and C has a supply of 5? Well, this is actually also possible. So there is a way of using only the arcs that are highlighted to convey, although not feasibly, to convey flow from C to B. I just sent it in the wrong direction. I mean, that would result in this arc BC having a flow of negative 5, but I'm allowed to assign non-zero flows to any highlighted arc, and this is a non-zero value. It's not feasible, but it is a solution to the problem. It does balance the flow. So here, I send flow backwards along the edge BC, and it goes from C to B. And as a result, it balances the supply of 5 with this demand of 5. So in this case, this set of edges is still valid for that. But what about this situation? So what if I put on vertex B a supply of 10, and on vertex E a demand of 10? And that's the only flow, and that's the only supply and demand imbalance in the entire graph. Everybody else is stuck at 0. How do I get 10 units of flow from B to E? Well, I don't. There's no bridge. There's no way to get from B to E using only the highlighted edges. That means that there is no solution for this equation for A, B, X, B equals B. There is no solution to this for this particular supply and demand assignment. And that means that this collection of edges is not a basis. So we're beginning to see the condition and how to enforce it or check it using only the graph, using only the edges themselves. So here's the same example, the negative example that the slides wanted to do. Consider this collection of 7 edges. Is this a basis? Now the slides are going to do the same thing I just did, which is they're going to start with some examples to give us some hope, and then just, wrench all that hope away from us by giving us an example that breaks it. So we'll start with this. If D has a supply of 5 and H has a supply of -5, then I can just push 5 units of flow all the way from D to H. That sounds good. So this collection of edges has passed the test so far. If I have this situation where H has the oversupply and D has the demand, okay, well that's not ideal, but I can, using only the highlighted arcs, I can still get flow from H to D. I just have to go backwards, which again, not feasible, but is balanced. So I send flow backwards from H to G, from G to F, from F to E, and from E to D. Okay, so that balances the flow there. What about this situation? Can I get flow from A to D? Absolutely not. Whether I'm going forwards or backwards, I would have to set one of these arcs to have a non-zero flow value, which isn't allowed. Only the arcs that are in the basis can have a non-zero flow value. And because there is no way to equalize this in this case, that means that this collection of arcs, these 7 arcs here, do not comprise a basis. And so because there is no solution, there's no way of producing a balanced flow, then this matrix, whatever it is, notice how we never actually had to construct the matrix to demonstrate this point. This matrix AB can't be invertible. If there is a vector B, a valid set of supplies for which there is no solution, then the matrix can't be invertible. Therefore, this is not a basis. Now, on the other hand, this is. Now notice I made only a relatively small change. I got rid of, I swapped a couple of edges here. I swapped these two and then I added this one. And now if I plant some supplies and demand, so F has, let's say, a supply of 5 and B, well, let's say A has a demand of 5. Well, let's see, I just have to push 5 units backwards along this edge, 5 units backwards, 5 units backwards, 5 units backwards, and I've balanced the flow. Suppose that B had the demand. Okay, well in that case I push 5 units backwards to A and then 5 units forwards from there to B, but I can still balance the flow. And if you stare at this for a minute, you might realize really what we need for a collection of edges to be a basis, to not have this problem show up, really what we seem to need is a notion of connectivity. So that way there's no, if my set of edges is in a sense connected, if there is a way of using only the edges I've selected to get between any 2 vertices, then there should be a way of equalizing any supply imbalance. Okay, so that means that maybe what I need in a collection of edges is some form of connectivity. And if you think back to the previous lecture, I mentioned that often the connectivity that we seem to care about in this application isn't the kind of connectivity you'd typically care about for a directed graph. It's sort of weak connectivity. So because we can push flow backwards along an edge, we don't really care whether the set of edges is connected in the fully directed sense. We just care if there's some way, even if we have to travel in reverse along an edge, to get from any vertex to any other vertex. And so basically the observation we're making is if you give me a collection of edges B, for that to be a basis, it appears to be required that this subgraph of all of the vertices, but just those edges, that subgraph be connected. I should actually say weakly connected because it is still a directed graph. Because if it weren't, so for example, if there were a vertex up here, so I guess that's vertex I, if there were a vertex up here that's connected only by basic edges or non-basic edges, then if it had a supply imbalance, how would I resolve it? So I need there to be connectivity because I never know where the imbalance is going to show up. And I need there to be some path between any pair of vertices so that I can resolve any supply imbalance. And it turns out that this conclusion that any collection of edges that's a basis must be connected gives us enough information to basically completely characterize what a basis has to be. Because we know already the number of edges in the basis. It has to be this number, the size of V minus 1. And it has to be connected. And if we think back to CSC 225, we might remember that if I have this number of vertices and I have this number of edges and the graph is connected, it has to be a tree. Period. That's it. These 2 facts together force it to be a tree. And therefore we can conclude that the set of basic edges, if I hand you any valid basis for my graph, that must be a spanning tree of the network. Keeping in mind from the previous lecture, in this topic, when I say spanning tree, yes, I get that this is a directed graph and we don't know what spanning trees are. I mean a spanning tree of the underlying undirected graph. Now, it turns out as well, this is something we can prove, but I think it's sort of intuitive. If you give me any spanning tree, so here's a spanning tree, if you give me any spanning tree, then any supply imbalance I come up with that meets the basic criteria that the network is globally balanced. In other words, if the set of all supplies in the network equals the sum of all of the demands, let's try this. If you give me any supply vector, so any set of vertex supply values that sums to 0, then any spanning tree whatsoever will automatically be a basis. Because since it's a spanning tree, there is a path between any two vertices, so there will be a way of equalizing supply and demand. How do I do that here? Okay, so I send 5 from G to H. I send 15 from H up to E. I send, I send 5 of those up to F, and then I send the remainder, 10, backwards from E to D. So you give me any spanning tree, and because there's a path in the spanning tree between any two vertices, I can equalize any sets of supplies and demand under the basic condition, obviously, that the global supply and demand is in equilibrium. So we can demonstrate this as well. Now, of course, keep in mind that just like in this example where I had to send flow backwards, this -10, just because something is a basis doesn't necessarily mean it's feasible. So a basis being valid means the matrix is invertible. It means there's a way of equalizing flow, of producing a balanced flow. Once we have a balanced flow, then we can begin talking about what we have to do to make that basis feasible, to make every flow point in the right direction. So that's what a basis is. If I hand you this network flow problem, a basis is a spanning tree of the graph, and that's it. We don't even need to worry about the linear algebra behind it. It's a spanning tree of the graph. Now, that said, suppose I hand you a spanning tree of the graph. I said, here's a basis. So we can now say, given the basis shown above, we can verify this is indeed a spanning tree. Given the basis shown above, compute the balanced flow. So compute some way, even if it's not feasible, compute some way of balancing all the supplies and demands with only the basic edges. So assigning a flow of 0 to all of the non-basic edges. Now, maybe we saw a minute ago sort of how I could do that. And certainly I could do that by solving this equation. I could compute my vector B, I could compute the matrix AB, and I could solve that with some algorithm to solve systems of linear equality, like an LU decomposition, or I could invert a matrix or something. And we can recall from last week that would take, I don't know, n cubed time. What I want to demonstrate is that there is actually a very intuitive way to compute it using only the graph, using graph algorithms effectively. And moreover, because it turns out that we only care about this spanning tree, which is a tree, we can use tree-based algorithms. And often tree-based algorithms end up being very linear, especially if we represent the tree the right way. If I represent this tree the right way, I actually can find a way of computing the flow across all basic edges such that the result is balanced. I can compute that flow in linear time using effectively what would amount to sort of a post-order traversal if I consider the spanning tree as being a rooted tree with A being the root. So recall, of course, that given a choice of basis, there is exactly one assignment of basic variables that meets the constraints. That's true. That goes back to last week as well. It's just the solution to this system of linear equations. I'm going to show a way of computing this solution using the graph, using a tree-based algorithm, instead of having to solve it with linear algebra. So the basis is a spanning tree, and there are lots of ways of thinking about this. So it's a tree in the most broad sense, a so-called free tree. So a free tree is just any connected acyclic graph. It doesn't have to have a root to be a free tree. I could just compute my flow values by working inwards from every leaf. So here's a leaf, here's a leaf, here's a leaf, and here's a leaf. I could just work inwards, because you might notice that because these are leaves of the tree, if E has a supply imbalance, so E, for example, has an oversupply of 3, and I'm only allowed to send flow out using this edge, clearly any oversupply has to go along this edge. And that's true of all leaves of the tree. So I could just work inwards from every leaf. Now, on the other hand, because we already have chosen a particular vertex to be special, to be the root, and we've even gone and called it a root, maybe it's nice to think about this as a rooted tree, to think about the tree starting at A and working sort of downwards from A. The reason why I like this interpretation is, first, it lends more significance to this idea of a post-order traversal, whereas if you consider it as a free tree, you're sort of doing BFS or DFS or something. I can view this as a post-order traversal, and also because when we get to talking about the dual values, we do need to consider it using a rooted tree. So I'm going to do this with a rooted tree representation, but there are lots of variants of this algorithm, not all of which use this idea of a root. So here's what I'm going to do. I'm going to work my way up the tree, starting at the leaves that are furthest from the root and working my way back up to the root. Now remember that conceptually there is no balance constraint on the root, even though of course it does get enforced by default because of the global supply balance that I expect to hold on the network. Oh, but the example got started without me. Okay, so I'm not going to show, I'll skip through the slides version of the example in a minute. I guess I want to try and work it out by hand. So the way the algorithm works is like this. I first find the leaves at the bottom of my spanning tree, so the ones that are furthest from the root. And then I observe that because each leaf, because it's a leaf, only has one edge incident to it in the spanning tree, that edge must carry all of the flow that is needed to equalize that node. So as I said earlier, E has an oversupply of 3. But I have to get rid of that. To be in equilibrium, it has to have 0, which means I have to send all 3 units over to D. Okay. C, as it turns out, is quite affable here. It's just got a 0, so I just leave it, and I send 0 units to B. There's no need to equalize anything there. D has a demand of 6. And to equalize that demand, whoops, I have to send 6 units to D. I mean, I've got to figure out where I'm going to get those 6 units from, but certainly I have to send 6 units to D. Okay, so now D, E, and C are all in equilibrium. They all have, assuming I can find a way of rectifying the accounting here, I have a way of getting them all the flow they need and getting rid of any oversupply. So what's B looking like? Okay, so B already had a demand of 2. And I sent in 3 new units, so now it has a supply of 1. But then I sent out 6 units, so it has a demand of 5. Okay, that means that, well, all of these edges, everything over here has already been determined. So I can't pull in any more flow from over there. So any flow that B needs has to come in from above, which means I have to send 5 units from A to B. And that means B is in equilibrium. And we don't care formally about the constraint on A, but notice that actually A is in equilibrium as well, by default. Because the system was overspecified, I don't actually need to enforce that constraint for that constraint to be met. Okay, now the slides are going to do the same thing. Okay, so my spot check here is 6, 3, and 5. Okay, so we'll walk through it. There it is, 6, 3, and 5. That looks good. The slides have some patter here that you can read when I post them if you want to go through the example later, but I'll skip over it for now. And so if I look at the resulting flow values, they are balanced. And moreover, if you think about the way this was implemented, what I was really doing is I was recursively starting at the root of my spanning tree and going down. And for each node, I would say, okay, first recursively handle the balance at the child nodes, and then come back up to the node that I'm standing on and rectify, equalize everything that came in from the children. So for example, I've got 0 units coming up here, 3 units coming up here, 6 units going out, and a demand of 2. Just balance those all out, figure out how much I'm missing, and have that sent in from the parent. All right, what about this one? This is also a basis. So it is a spanning tree of the graph. If I look at everything, it is definitely a spanning tree of the graph. So I should be able to compute the flow values for this as well. Okay, so this is my root. So I work my way down the tree from the root, and I start at the leaves and work my way back up. Okay, so D has a demand of 6, which means I have to send 6 units from E to D. All right, now C, again, C is just so easy to get along with here. C has a demand of 0, so I just send 0. Who cares? Okay, but what's going on at E? Okay, so E had a supply of 3, but then I sent 6 units to D, which means E is now down by 3. E is now at a deficit of 3. So somebody has to send 3 units of flow to E. But how are they going to do that? Right now, there's no way of getting anything from B to E. I mean, I want to send it from B to E, but there is no arc from B to E. It goes in the wrong direction. So remember that balance is more important than feasibility at this step. Given a basis, I have to know the flow values to know if it's a feasible basis. So what I want to do is send 3 units from B to E. In other words, I want to send negative 3 units from E to B. I want to send flow in the wrong direction across the edge EB. Okay, so I do that. So that means that there are now 3 units of flow leaving vertex B, and going to vertex E, which means vertex B, which already had a deficit of 2, is now at a deficit of 5, just like before, which means I have to send in 5 units from A. And that puts all vertices in equilibrium, and of course, all of the balance constraints are now met. The problem, of course, is this. We'll figure out how to resolve infeasibilities later, but this is the set of flow values that would correspond to this basis. Okay, so we'll just skip the pattern. There we go. We end up with this. I think that's a typo. I'm calling that a typo there. That should be 5. So I'll fix that in the posted version. Nope, still 5. The typos on 2 slides. Now, I get that it seems a bit weird that we're doing this. Like, why are we trying to compute these flow values that are negative? What we need is to know, given a basis, if I say I insist that this set of edges be my basis, I need to know what flows go across those edges. And I need to know if they're feasible or not. So I have to compute them. If I compute them and discover that they're infeasible, then I need to do something about it later. And that might be where I perform some kind of a pivot. So if I notice a set of flows that's infeasible, if I have flow values like this one that are infeasible, this would be a primal infeasible basis. But maybe I'm running the dual simplex method. I might just do a dual pivot here. But I need to know the flow value before I know what I'm supposed to do next. Another thing to note, of course, is that this vector xb, so what I'm doing, these values that I'm putting on the edges here are actually the individual, this would be the value of xed. I'm computing the values of this vector xb. I could, of course, just compute this by solving the system of equations, abxb equals b, and the key thing to note here is this -3 that I'm so worried about, I'd still get it if I computed the answer this way. I just do a lot more work solving the system of equations. All right, so here's a more complicated example. So this is one of our running examples from earlier. It's pretty complicated. It's hopefully complicated enough that we can see this algorithm in action and we can agree that it probably does run pretty quickly. So here's my root. It's vertex A. I would like to compute the balanced flow corresponding to this particular basis. So what I do, just like before, is I work my way up from the leaves. Okay, so I can see a few leaves here. I may not hit them all in the most methodical order, but okay, there's G. So G has an oversupply of 10. It has to get rid of 10 units. I guess it has to send all of them down to F. Okay, what's the next one? I think the next one is, well, okay, H. So H has a demand of 6. Somebody has to send H 6 units of flow, and I guess it has to be vertex I. All right, so we'll come back to I in a minute. Okay, so what about vertex D? Vertex D is a leaf. It's down here. Vertex D has an oversupply of 3. Oh, that's too bad. So somebody has to take 3 units of flow away from D, and the only arc available is this one. So I have to send 3 units of flow to E. In other words, I have to send 3 units backwards along this edge. So we'll put that value as -3. Okay, what's the next one? The next one is vertex C, and well, vertex C is just such a nice... So vertex C, of course, has a demand of 0, so I just send 0. Okay, well, that makes my life easier. Okay, where do I go next? Let's see. So vertex I is now ready. Everything below vertex I has been handled. So vertex I had an oversupply of 1. But then I sent 6 units away, which means vertex I is now sitting at a deficit of 5, which means somebody, and of course this has to mean vertex F, somebody has to send vertex I 5 units of flow. Okay, so what about vertex F? Okay, vertex F had a demand of 2, but then I sent in 10 units from G, so it now has a supply of 8. But then I sent out 5 units to I, which means F now has 3 left over. And I have to get rid of all 3 of those units of flow, and the only edge available is the one leading up to the parent of F, which is E, so I must send 3 units from F to E. Now, if we look at vertex E, you have to be a little bit careful here. So at vertex E, there was originally a supply of 6. And then I received 3 units from F. So E now has a supply of 9. And we have to be a bit careful about this negative number here. So I'm sending -3 units to D, which means I'm actually receiving 3 units from D. So my net supply is now 12. E has actually received new flow from both F and D. So E now has an oversupply of 12, and it has to get rid of all of it, which means it has to send all of it up the tree to A. And of course, that requires sending it backwards along this edge. So I send -12 from A to E, or 12 from E to A. Okay, and then finally, what's going on at B? So B has a demand of 6. Somebody has to send vertex B 6 units. Unfortunately, the only direction is the wrong one, so I'm going to send -6 from B to A, or send 6 from A to B in reverse. And if I stare at this for a minute, I will notice that actually the system is balanced. So A is, every other vertex was balanced. We verified that for every vertex below A. If we look at A itself, A is receiving 12 units this way, in reverse, and it's sending out 6 units this way. And A has a demand of 6, and those do balance out. So it turns out every vertex is now in equilibrium. hopefully if you stare at this for a minute, you can see that what I had to do there was pretty straightforward. It was pretty much a linear time thing. I handle each vertex once, assuming I have the tree stored already. So computing the tree is not necessarily linear time, depending on the number of edges in the graph. Once I have the tree, I can ignore all the non-basic edges. So once I have the tree, the number of edges of the tree is linear in the size of the tree. And so I could actually compute this in linear time. And the slides are now going to go through this too. Okay, good. So I have this, and we can move that. Yeah, okay. I got a duplicate slide there. So the next question is, I guess, we have a way, if you give me a basis, to compute the primal flow values for each edge in the basis, such that balance is met. Now, feasibility might not be met, so these are not feasible, but balance will be met. We will have equilibrium of supply and demand. That is how we handle our primal variables. We saw in the previous lecture that in this style of LP, there are no slack variables to speak of. The primal slack variables, if they exist, are completely useless. They are ballast. So there's no point in trying to figure out what they mean. On the other hand, maybe we should talk about the dual variables. So we know, for example, that in any LP, if I've got a set of basic primal variables, so for example, in this example, xgf would be a basic variable because it's carrying a non-zero amount of flow. The basic primal variables will correspond to some dual slack variables, which we usually call z, but we know that by complementary slackness, if the primal variable is basic, then the dual slack variable associated with it is non-basic, which means it's 0. On the other hand, this non-basic arc, so the variable xhg, is non-basic. And that means that there might be an associated dual slack variable. Now, similarly, because we have one constraint in our LP for each vertex, we should expect that there will be one dual variable that corresponds to each vertex. We'll call that y. And I want to know, not just do these variables exist, but what do they mean? Can we interpret them in graph theoretic terms? And that's the question here. So we'll go back to our smaller network example and talk a bit about that. Now, to do this, we'll have to talk about what the dual actually is. So here is our primal LP. And we've got this one row that there it is, we can see it, but it's been deleted. For the sake of actually solving the LP, this row really isn't there. But it's good to stare at it. It's good to have the row there so that we have some point of reference when we compute the dual. We saw, and I'm just going to, I'll skip over this and come back to it. We saw in part 1 that we can construct a dual of an LP that looks like this, and we end up with this form here. Or I guess that wasn't part 1. That was actually a full lecture ago. So one lecture ago we saw this, that after a bit of rearrangement, the dual for an LP that looks like this will look like this. Notice that in this dual, I've actually highlighted the column corresponding to that deleted row. Because this column, just like how this row really isn't here, this column also really isn't here. And I'll explain in a minute how to parse that, given that there's apparently a variable that we need to care about. I'll explain that in a minute. What I will observe is, in our dual, we've got this set of, we now have one column per vertex and one dual optimization variable, y, per vertex. But we also have one of these dual slack variables for every arc. Now, just to be clear about the formatting here, there is a different dual slack variable associated with each constraint here. There's one per arc. I've written them all in one column because the LP would look obscenely wide if I tried to put them in separate columns. So that's where we end up. Now I want to skip back to the slides that I jumped over. So we know that each of our constraints in the primal LP represents the balance of one vertex. And we know that because of the way duality works, that means that there will be one dual variable for each of these constraints. One dual optimization variable, one of our y's. And it'll correspond to that vertex. This is the row for vertex A, so we'll call that variable ya. We also know that because of the way duality works, again, we've got these primal optimization variables xab, and there should be a corresponding dual slack variable zab as well. And we also know we already know a few properties about the relationship between them, which is that by complementary slackness, exactly one, for a particular arc, exactly one of xab and zab can must always equal 0. They could both equal 0, but exactly one of them at most can ever be non-zero. And so we can rephrase that. For a particular edge, uv, at most one of xuv and zuv may be non-zero, but we know already the relationship between basic, primal, and non-basic dual variables, and it turns out that if my arc uv is a basic arc, then zuv has to be 0. The dual slack variable has to be 0, because if the arc uv is basic in the primal, then the arc uv will be non-basic in the dual. And similarly, if the variable, if the arc uv is non-basic in my primal LP, well, obviously then xuv is a non-basic variable, it has to equal 0. So here is our dual. So back to this. Remember that from the previous lecture, that because of the strange way that we have to compute the dual of an LP with only equality constraints, we end up with no non-negativity constraints on the y variables. So formally, we could write that, although we don't have to, we could write that as this, to explicitly indicate that each y variable is actually fully unconstrained. There are no associated non-negativity constraints. On the other hand, the dual slack variables are required to be non-negative. So go back to the previous lecture, you can take a look at the derivation there, or the result of the derivation, for why it is that for some reason the dual slack variables do have to be non-negative, but the y variables themselves can be positive, negative, or 0. And this means, just to be clear, I mentioned this before, that in an optimal solution, or a feasible solution, all I require is that the z's and the x's be non-negative. The y's can be negative in a feasible solution as long as all the constraints are still met. And one note for later is that when we eventually get to talking about optimal solutions, what we care about, we know from duality, is that an optimal solution is any solution that is both primal and dual feasible. So primal feasible, we already know what that means. Primal feasible means that each of my primal flow variables, xuv, is non-negative. But because there are no constraints on the y's, the only thing I need for the dual, for dual feasibility is for the z's to be non-negative. It doesn't make any difference what the y's are. As long as it's feasible, any solution that has the x variables non-negative and the z variables non-negative and the constraints met is a feasible solution, primal and dual. So if we get one that's both primal and dual feasible, that is our optimal solution. We'll need that later because we're going to use that as our barometer of optimality. We're not going to have a dictionary because we're going to be working with a graph, so we need some way of knowing when we're looking at an optimal solution. And duality hands that to us. It says if you have a primal and a single basis that is both primal and dual feasible, that is optimal. And then finally, there's this. So we had that one row of our primal LP that we deleted. We deleted a row that was overspecified. And then we computed the dual. And of course, if we deleted the row, really, this column isn't here at all, right? Like, it's just not there because we computed the dual of an LP that didn't have the row that corresponds to that. On the other hand, it's good to know that this column would exist if we hadn't deleted the row, because we want to see the correspondence. We know that if we go way back, this is the full system of equations that we derived. We deduced that we don't need one of the equations, but we still care about the, interplay between the different equations. So what do we do to the dual to try and ameliorate this? Like, what do we do to account for this column being missing? One thing that I think is important is, it's true that there really is no variable ya. Like, really, this column isn't really here. There is no variable ya, but for consistency, for the sake of having a y for every vertex, it would be nice to make one up, to define a notional ya. On the other hand, we can't go around adding variables to our system if it's going to break something. We have to make sure that if we make up fake variables, that it makes no contribution to anything. So what I'll do is this. I'll say, how about this? We will define y sub a, a is the root. Remember that you could choose any vertex to be the root, but in this course we will choose vertex A to be the root. So this is vertex A. We're just going to define y sub A to be 0. So every vertex will have an associated dual variable, but we're going to adopt the convention that at all times ya, the one corresponding to our root, will always equal 0. And you'll notice that if you do that, then it does have the same effect if we consider the whole system as if ya weren't there at all. Because if it equals 0, it just makes no contribution to anything. Now, the reason that we chose that root vertex was to make the basis matrix invertible, and it doesn't participate in the constraint system, and so we'll just make up a phantom variable ya. That's what I just said, I guess. Okay, so I guess I got ahead of myself. And we will treat that to basically always equal 0. And I'll explain in our construction in a minute for how we actually compute the dual variables, why that's actually a pretty easy step to take. So the question now is, suppose I hand you a basis. And remember that by this point in the lecture, if I say the word basis, you should think spanning tree. To be a basis, it must be a spanning tree. If I hand you a basis and I tell you what my root vertex is it possible to figure out the values of all of my y variables? So know that, recall that for a particular basis, I can definitely compute the values of my x variables. We just did that. We can compute the balanced flow corresponding to a particular basis. The question is, can I do the same thing for the y variables? And it turns out that the answer is actually yes. So let's stare at this basis for a minute. So the basis here is are the arcs AB, BD, EB, and CB. And now let's just go back and stare a little bit at this system of equations. I'm realizing in hindsight I should have put them side by side, but sorry about that. So I'll write it down. So it's AB, BD. So suppose that we are just the arc AB. Suppose that AB is basic. So what do we know? Well, we know then if AB is basic, then by complementary slackness, that implies that, so ZA or XAB, there could be flow along arc AB, but if AB is basic, then ZAB, the corresponding slack variable, has to equal 0 by complementary slackness. So I know that the arc AB is basic, and that means I know that ZAB equals 0, which means I can just ignore it in this line here. I stare at this for a minute and I say, okay, so I know that YA equals 0, and I know that ZAB equals 0, which means that, hey, I have the value of YB. YB equals 1. Well, that was nice. Okay, what else is in our basis? Let's see, the arc BD is in our basis. So BD is basic. And that means that ZBD has to equal 0. Okay, so can I figure out the value of YD? Well, let's see. So I know what YB is. It's 1. So this is just 1. So that means that -1 plus YD equals 1, which if I solve that for YD, I'm really saying that YD equals 2. And if you think about this, what you might notice is that if I can start at the constraints that involve my root vertex, which I know has a y value of 0, and I can keep in mind that for every vertex, there will have to be at least one edge attached to it that's basic, which means the z value has to disappear, I should be able to solve my system of, I should be able to solve this system of equations for the y variables and find their values, just iteratively. So starting from the root and working my way outwards. So I started with this constraint involving a and b, and then I worked with b and d, and I could work my way down the rest of the constraints that way. So I could do that. And actually, I mean, moreover, what I could do is use linear algebra. I could solve a system of equations given all these conditions. And so that means I can definitely compute each of my dual variables. But there's another way of doing it. There's a tree-based way as well. It's more of a pre-order traversal of a tree, not the post-order traversal we would have used in the previous case. But not only is it nice and fast, it also can be done in linear time once you have the tree, but it also exposes a really interesting property of the dual variables, a way of giving them actual meaning as opposed to just something that falls out when you compute a dual. So to be clear, all of what I'm about to show is actually just a way of interpreting this system of equations, of keeping in mind that certain of the z variables have to be 0, and that since ya equals 0, we can use that to iteratively deduce the values of my y variables. And we could, again, just do this all with a system of equations. And what we're relying on is the fact that every vertex, so here are all the edges affecting vertex B, every vertex has to be incident to at least one edge, which is basic, which means the corresponding z's have to go to 0. And that's the idea, is that we can start at the root, where we know that the y value is 0, and work our way down the tree from there, keeping in mind that because in my primal LP, every column corresponded to one edge, and therefore had only two non-zero values, every row will contain only two occurrences of a y plus a z. And that means if I can get rid of the z, if I find that certain z's are equal to 0, I can iteratively solve by finding one of the y values, I could find the other one. So we could do that with linear algebra or whatever, by inspection. We can also do it with the tree itself. And the idea is, unlike in the primal case where we worked our way upwards from the leaves, here we are going to work our way downwards from the root, because we know that y sub a equals 0. So we already know the dual value for our vertex A. So the question is, if I hand you a particular basis, can you compute the value of each dual variable? And on the one hand, the answer, it turns out, is obviously yes, we can do that. We can do that by reverse engineering that system of equations. What we're going to notice very quickly is there's an interpretation we can come up with that makes it even easier to compute. Okay, so what we're going to notice as time goes by is that our right-hand pane is going to get more and more complicated. By the time we're done this lecture, we're going to have tons of information in the right-hand pane. We're going to have flow values across each basic edge. We are going to have dual optimization values, which we'll write underneath each vertex. This will be the value of YA. This will be the value of YB. And we're also going to write the dual slack values, which we know are always going to be 0 for basic edges. We're going to write the dual slack values on our non-basic edges. And that's going to be our complete tableau, the equivalent in a sense of the dictionary for our network simplex method. Okay, so the root vertex A has YA equals 0. This is because we have defined it to equal 0. Vertex A actually doesn't really have its own organic Y variable. We've made one up and given it the value 0. And then we stare at these individual constraints of the dual problem. And we say, well, so if I have a particular edge, UV, so it starts at U and goes to V, then the constraint in the dual will look like this. And you may recall in the previous lecture, there was a point when I said something like, we're going to choose to negate both sides of one of these equality constraints. Trust me, it makes the dual easier to understand later. And what I meant was, I think the signs here would be backwards if I didn't have this, and it would make the resulting number a little bit less easy to understand in a couple of slides. So that's where this slide is where that transformation is now paying its dividends. So an arc from U to V will result in this constraint in the dual, which is the negative of the dual optimization variable for the source vertex, U, plus the dual optimization variable for the destination vertex, V, plus the corresponding dual slack variable for the arc, equals the cost. If the edge UV is basic, in other words, if I'm walking along the edges of the tree itself, then I know that all of the Z values have to be 0, so I can just ignore this. And now I observe that means that if I'm walking down my tree, because I start by knowing the value for the root, if I then walk down my tree and I look at each arc in the tree, at each step, exactly one of these two values will be known. I don't know which one in particular, because I don't know which direction the arc actually points, but one of the values will be known, and so I could just solve the equation for the other one. And therefore, I can just work out the value of each dual variable by moving down the spanning tree from the root. But the astounding observation to make is, once I actually solve these equations, what I will realize is the dual optimization variable associated with each vertex will equal the total cost of moving one unit of flow from the root all the way to that vertex. And that's the interpretation I'm going to use to complete the algorithm. So it turns out that the dual optimization variable for B, the value of YB, is 1. And we actually figured that out earlier when we were looking at the constraints themselves. The dual optimization variable for for D, Y sub D, is going to equal the value for B plus the cost of this arc, which is going to be 2. And notice that if I were to try and ship 1 unit of flow from A to D using only the basic arcs, how much would it cost? Well, let's see. 1 to get me from A to B, 1 to get me from B to D. And it turns out that's what the dual optimization variables are. They give you the total cost of moving 1 unit of flow from the root to each vertex using only the basic arcs. With one caveat, and it's going to be a weird one, you're probably not going to like it, which is that if I have to work in reverse across an arc, the cost gets negated. So that is to say, if I'm going to compute, I already have the value for D, it's 2. If I want to compute the value for E, okay, so from A to B costs 1. From B to E is going in reverse. So I'm going to interpret that as meaning -8, which means the dual optimization variable for E, the value of YE, is going to be -7. And you'll stare at that and say, what the hell is going on? Why are we allowed to assume that we make a profit by moving something in reverse along an edge? There are a couple of things I can observe here. One of them is that we're only ever going to care ultimately about feasible flows, and that means that we're never going to be actually moving stuff in reverse once we're looking at a feasible basis. So we could argue this is just a necessary compromise in the meantime. The other thing to observe is that consider the fact that if I model the edge EB as like a road between two cities, at any given time, I could be shipping like 20 million things from E to B. When I say, for today, I want to send something in reverse, what I really mean might just be send, 10 fewer units in the forward direction. So it could be that all along I was sending lots of flow between cities. And when I talk about sending, 10 units in reverse, what I might just mean is don't send 10 units forward. And so in a sense, I'm saving money by not sending 10 units. And so there is a a reason why modeling that as a negative cost does make sense. What I'm really saying is don't ship something in the forward direction. And if you shipped it in the forward direction, it would cost 8 units. So if you don't ship it, you save 8 units. So either way, in any case, because we're not going to end up with a feasible basis if something goes in reverse, it doesn't really make that much of a difference how we interpret cost in a sort of an economic sense. The idea, though, is that for this interpretation to work, where I derive the value of each dual optimization variable, the value of a dual optimization variable is the total cost of shipping from the root to that vertex using basic edges, assuming that if I ever go along an edge in reverse, the cost of that edge gets negated. So I end up with this. And of course, the cost of getting to C. C is just so, for some reason, C is a bit of an enigma in these series of examples. It costs 1 unit to go from A to B, but then I save 1 unit by going in reverse from B to C. So C actually nets out to 0. All right, so I have this algorithm that allows me to compute my dual optimization variables starting at the root and working my way downward. And even better, I mean, the algorithm is nice, but even better, I've come up with this fantastic interpretation. I now have a semantic meaning associated with each dual optimization value, which will really come in handy when we begin talking about pivoting, about what it means to pivot. It'll turn out a pivot involves taking one arc out of the basis and putting a different arc in. All right, so we'll go back to our longer example here. The question is, can we compute the dual variable values for each of these vertices with this basis? So it's actually the same basis as earlier. The key thing is, unlike earlier, we're not going to be starting at the leaves and working our way up. We're going to start at the root and work our way down. Okay, so the root has, and actually we should visit for a moment this interpretation in the context of the root. We know that the root, the value of ya at our root, is always 0. But on the other hand, that fits our interpretation pretty well too. What is the total cost of shipping 1 unit of flow from the root to itself? Well, just 0. It just stays there. So in a sense, our phantom variable ya fits perfectly with our interpretation. Okay, so we'll work our way down the tree from our root A. Okay, so what is the total cost of shipping from A to E using only basic edges? Well, it looks like it's 1. Okay, what is the total cost of shipping from A to B using basic edges? Well, the problem is I have to go in reverse along this edge, so it's going to equal -1. I'm going to end up actually making a profit sending something across this edge. And similarly, if I want to go from B to C, well, it costs 1 to go from C to B, so it costs -1 to go in reverse. So I'm already at -1 to get from A to B, and then I'm at -2 to get from A to C. So remember that the dual optimization variable is the total cost from the root all the way to that vertex. Okay, what about up here? So from A to E costs 1. From A to D will cost 1 plus whatever the cost of this arc is. It's 2. So the total cost here will be 3. All right, what about from A to F? Well, from A to E costs 1, but from E to F I have to go in reverse and it costs 2. So the total cost will net out to -1. From A to G, well, okay, it's -1 to get to F, and then it costs -7 to get all the way up to G, and if I add those together, I end up with -8. From A to I, well, from A to F is -1. From F to I costs 15, which balances out to 14. And then finally, from A to H is going to cost me 14 to get to I, plus the 4 it takes to cross over to H, and that's going to add to 18. So there are my dual optimization values. Now, your mileage may vary as to what you think about the weird negative cost thing, but hopefully in any case, you can agree that computing those things, starting at the root of the tree and working downwards, is pretty easy. If I hand you a particular basis, we now have a way of computing the primal flow values across each edge, whether or not they end up being feasible, and computing these dual optimization variables, the total cost of shipping something to each vertex using the basic edges. And we'll let the slides now catch up with my, I'll do a spot check. Okay, so this is H is 18, C is -2, and F is -1. So let's see if that ends up working out. Okay, 18, -2, -1. That looks good. Okay, so hopefully you can see this is the kind of thing where if you get this on an assignment or an exam, you do want to make sure you check your answer a couple of times because it's easy to make an arithmetic error, especially with those backwards arcs. But I hope you agree the algorithm itself is relatively straightforward. So what do we have? we have found, I think we've actually got some pretty, some reasons to be pretty optimistic here. We have found a way of converting a lot of these pretty abstract concepts, these properties of our simplex method, converting them to very intuitive aspects of the network, of the graph. So the first thing we saw today was that a basis of one of these network flow problems is a spanning tree of my network. We've seen, and this is less, I mean, was already sort of obvious, I guess, less of a revelation, that our primal flow variables, xuv, will correspond to the number of units of flow across that arc, across arc uv. And that because our basis is a spanning tree, there will probably be a bunch of non-basic edges, they will always have a flow value of 0. Now, to be clear, if you look back at the previous lecture, we even had an example of a flow that used more than a spanning tree of edges. It's perfectly valid to send flow across every single edge of a graph. The key thing that we have observed today is in the optimal solution that we're looking for, a spanning tree will be sufficient. There's no need to use any more edges than those in some spanning tree to represent an optimal solution. There could be optimal solutions that use more edges, but there will always be one that only uses the edges of a spanning tree. And then finally, we were able to derive that the value of each dual optimization variable for each vertex v, the dual variable yv, will equal the total cost of moving 1 unit of flow from the root to vertex v using only basic edges, assuming that if I follow an edge in reverse, the cost of that edge gets negated. There's only one thing left we need to have a complete interpretation, and that is, what about those dual slack variables? So we know that we don't care about primal slack variables. They're useless, they're ballast, but we do have these dual slack variables, and we know a couple things about them already. The first thing we know is that in the event that our arc uv is basic, then the dual slack variable will be 0. Okay, so that solves some of our problem. We've certainly been able to deduce a few of our dual slack values already. By the same token, we know that certain x variables are always going to equal 0 if the corresponding arc is non-basic. Now, as far as how to compute the z values, it turns out that we don't need some clever tree-based algorithm for this, because once we have the x values and the y values, we can just go through and by process of elimination, because we already know the y values, we can just solve each of our constraint equations for z. And we only do this for the non-basic arcs because we know already that for the basic arcs, the z value is 0. So as far as computing the z values, there isn't too much we need to do. We just go back through our graph, and once we have all the y values, and we know the costs of each edge, obviously, we can compute the z values. And so here's an example. So this would be the basis we had earlier. Here are the dual slack values there. And it shouldn't surprise us that they are very closely related to the dual optimization variables because the equations that define the z values use the y variables. Now, the question we should ask, though, is there something meaningful we can derive from this? Is z just some random number? Is it just something that falls out of an equation? Or does it actually tell us something? We want it to tell us something because I want to be able to use the values of my z variables to, for example, decide what kinds of pivots to perform. Because as you might recall from last week, we can phrase the entire simplex method in terms of look at the x variables, look at the z variables, and use those to decide whether we're looking at a primal feasible or dual feasible solution. And then if we aren't, choose a pivot from the x's or the z's. In particular, choose a primal infeasible or dual infeasible variable and use that as part of a pivot. So it would be nice to have some idea of what these z variables actually mean. And there is an interpretation. It's a little bit more abstract than the other variables, but I think it's an interpretation that we can benefit from, which is if we take a look at one of these dual slack variables, what it tells us, so I'll use the one, let's look at vertex, let's look at the value of ZED. So ZED here is equal to -4. What we can do is view the value of ZED as being the increase in cost associated with getting flow to vertex D via this arc, the non-basic arc associated with the dual slack variable, instead of however it's already getting there. So in this basis, we're assuming that if I want to send flow to vertex D, I send it through the spanning tree, so this way. Suppose I were to send flow to vertex D through this arc. So in other words, I get the flow to the source of the arc, to vertex E, and then I go from there to vertex D. The value of Z is going to tell us how much will the cost increase if I do it this way versus using the current basis. And notice that because it's negative, what that's telling us is that it will be cheaper. The cost will go down if I send my flow to D this way instead of sending it to D this way. Now, this is when I say more concretely, this is just made up notation. Don't worry about ever using this notation again. I just want some way of writing it down concretely. We're never going to use these p variables I'm defining here. I just wanted some way of writing this out as an equation. So the value of Z is going to equal the cost of transporting one unit of flow to vertex U and then on to V using the non-basic edge UV minus the cost of transporting one unit of flow from the root to V the normal way using the basis. That means if I discover that this Z value is negative, then it's cheaper to transport flow the long way, transporting it first to U and then along to V using the arc UV, than it is in the current basis. What that's really telling us is that edge UV, if we add it to our basis, could give us some cost advantage. In other words, we might get a lower cost basis if we do that. And that might make some sense, because if ZUV is negative, then we're looking at an arc that isn't dual feasible. In other words, an arc that might be a good entering variable. However, that might still be very abstract. Let's look at a smaller example, and maybe that'll help us make it more concrete. So here I've got a very simple network with only one non-basic edge. Notice that the cost of transporting flow from vertex A, from the root to vertex C, is 11. So in this case, our variable PB equals 11. The cost to transport stuff to vertex C using only the basic edges equals 11. The cost to transport flow to vertex C, if I go the long way, if I use this, so this would be the value ZDC. If I want to use arc DC to get flow to vertex C, what I have to do is first get the flow to D, which costs 3, plus the cost of using the arc itself, which costs 2. So it costs 3 units to get to vertex D, 2 units to get to vertex C along the arc DC, and that means that the value of PDC equals, 3 plus, so 5. And that means that this equation, so with this sort of ad hoc notation, PDC minus PB equals 5 minus 11, which equals -6, hence the value -6. What that's actually telling us is that if I were to start transporting flow to C using the long way, so going through vertex D and arc DC, that would cost me 6 units less than if I were to use whatever method I already have in my basis. And if I were to do a swap, so it's going to, I guess the slides, I've gotten past the slides a bit. If I were to do a swap, I end up with this. If I put arc DC in the basis, then sure enough, the cost of transporting flow to C is now 5, because I just follow, it costs me 2 plus 1 plus 2 to get to vertex C. The value of ZAC is equal to 6, because the cost of transporting flow to vertex C using arc AC would be 11. And the cost of using the basis would be 5. And of course, 11 minus 5 equals 6. What this is telling me, because this is positive, is that if I were to use this arc instead, it would cost me 6 units more to transport flow to C than if I used my basis. It's a way of telling me that there's no reason I should put this arc in the basis, because it costs less to use the current basis. Conversely, if I'm back at this situation here, where I have a negative value as one of my dual slack variables, what that's telling me is that I could save 6 units. If I want to transport flow to C, I could save 6 units if I put this arc in the basis instead of whatever's already getting me to vertex C in the basis. And there's a derivation that works this out. You can take a look at this. I believe all these slides I skipped over are just a summary of the things that I said on that slide a couple of minutes ago. So the idea, though, is that if we ever see a negative value on a non-basic edge, that's telling us we can make our basis cheaper. We can make the cost of transporting flow to particular vertices go go down. And of course, that is related to our dual feasibility. This is a dual infeasible edge. Therefore, it's one we might consider as an entering edge, as something that should go in our basis. And that makes sense because it's going to save us money. It's going to save us cost, and our goal is to minimize cost. And any edge that will reduce our cost will therefore be an edge we should have in our basis instead. And we'll notice as we go forward in the next 2 lectures, we'll see how we define a pivoting procedure that looks at a non-basic arc and decides to add it to the basis, to make it a basic arc. All right, so we can now compute. Again, computing the dual slack variables doesn't tell it, like, there's no clever algorithm for that. We just walk through each constraint and compute it. If we compute the dual slack variables for every single non-basic edge in the example we went through earlier, we can now, for the very first time, see the complete picture of the simplex method on the graph. We now have everything that we need. We've got our basis. That's these red edges. I think it's going to say this. Yeah. The basis is the red edges. We've got the primal flow values along each basic edge, keeping in mind that the dual slack variable for IH will be 0 because it's a basic arc. Across each non-basic arc, we've got our dual slack value, and then attached to each vertex, we've got the y value. We've got the dual optimization variable. And we'll also observe that we know enough about the interpretation of these values to understand a little bit about what we're going for. So for example, we know this flow is not feasible. We're sending flow in the wrong direction across certain arcs. This is a non-primally feasible flow. We also know that this flow is not dual feasible. If I were to use arc DI, instead of, I guess, arc FI, if I were to use arc DI to transport flow to vertex I, I would save some money, because, I mean, we can see here it costs a lot to use arc FI. That's one reason I might want to modify my basis to use arc DI instead. And so what we'll begin talking about in the next lecture is basically, once I have a feasible basis of some kind, how do I make it optimal, whether it's dual feasible or primal feasible? And then finally, at the very end, once we've talked about both the primal and dual pivoting strategies, there is the question of, what if my basis is neither primal nor dual feasible? So I've got flow in the wrong direction, and I've got cases where cost could be improved. What do I do to start? How do I, for example, find some primal feasible basis and then do a bunch of pivots from there to produce an optimal solution? Okay, so just to walk through some examples there, here is an example of a primal feasible basis. So if all of the primal flow values are non-negative, my basis is primal feasible. So that's an example of a case where all of the flows are going in the right direction, but I may not have the minimum cost flow. And that would be where I want to do some pivots. So I'd say, for example, hey, I might save some money if I were to use this edge to transport flow to D instead of whatever other edge I'm already using. Now, we'll have to observe that it's not just a question of deleting this edge here. It might be that some other edge has to go, but I can definitely save some money if I brought this edge into the basis. I can minimize the total cost of my flow. The flow is feasible, but it's not optimal. Okay, so my flow is primal feasible if all of the primal flow values are non-negative. On the other hand, in a situation like this one, where this is not primal feasible because there is a negative flow across a certain arc, and maybe you can guess what I might do to solve that, there is a negative flow across an arc, so it's not primal feasible, but it is dual feasible. So although I'm not allowed to push flow in the wrong direction, if I were, this would be a pretty good solution, because there are no arcs I could bring in that would save me money. All of the non-basic arcs have a non-negative dual slack value. So it's a dual feasible basis. Now, by strong duality, if I ever end up with a basis that has positive values on everything, so all of them, or non-negative, sorry, all primal flows are non-negative, all dual slack variables are non-negative, and you can verify that that is the case here. So every variable attached to an arc is non-negative, then I have an optimal solution. It's both primal feasible and dual feasible, and that makes it optimal. Now, notice that in this optimal solution, the dual optimization variables can be negative, and that's allowed because the dual optimization variables in the dual are unconstrained. And so our next step will be, we now know what an optimal solution looks like. If we're staring at a particular basis, we now know how to test. Is it primal feasible? Is it dual feasible? Is it optimal? The question is, what if we're staring at a basis that is not optimal for some reason? So for example, it's got a negative dual slack variable, or it's got a negative primal flow variable. What do we do to make it a little bit better, to get us one step closer to that optimal solution? And the answer, of course, is pivoting. And so the next two lectures will talk about pivoting in the primal sense. So a primal pivot would be choosing a dual infeasible arc and bringing it into the basis. And in the lecture after that, we'll talk about dual pivots, which is choosing a primal infeasible arc and removing it from the basis. And by the time we're done talking about that, we will have derived the entire simplex method strictly in graph theoretic terms.